let's talk about the derivatives of vector function, okay? So this is not something new, okay? Think about like just two-dimensional vector function. It has x component function, comma, y component function, okay? Then whenever you want to find, let's say like if that function is r, then whenever you want to find r prime, just take the derivative of your x component and the y component separately. That is the derivative of vector function. That's it. Even I gave you like definition of these two, but like these are same thing. But as long as you understand about that definition for each function, and I mean like x component function and y component function separately, and that's enough. Okay. And we also know about the vector function, about the velocity function, right? And then we can write your r prime as the like basis like algebraic notation as well. Okay, which is x prime, which is x component times I plus y prime j, okay? If r is position vector function, then we know about the velocity function, right? Which is r prime, okay? What is r prime? X component prime, comma, y component prime, okay? And if you want to talk about speed, that's exactly the length of your r prime, which is square root of x component square plus y component square, okay? That's it, okay? These are everything same thing, but we will talk in vector, okay? Now let me give you one example, okay? Look at that. Your vector function r is given like this way, t comma t squared. We assume this is the position function, okay? So like if you want to find the position at parameter t, then just you can find position by plugging in t value, okay? Then now, how can we talk about direction? But I don't know, do you remember this one? But at the beginning of this class, this whole course, we already talked about the direction of motion, okay? By plugging in two different t value, okay? But since we know the a rate of change, which is r prime, and we can find the direction of motion by taking finding r prime, okay? So let's practice, okay? Here we go. First of all, to sketch the your vector equation, we have to use the parametric equation, okay? Here we go. Let me write this one as parametric equation, okay? Your x component is t, and your y component is t squared, okay? Let me do the substitution, which means I'm gonna substitute this one, plug into second equation, okay? Then you will have the Cartesian form directly. Your Cartesian equation is y is equal to x squared, okay? We know about the graph of this, right? So let me draw the graph of this function on the side, okay? Here we go. It is parabola, which is smiley face, because you have positive coefficient of x squared, okay? Smiley face and pass through 0, 0, okay? This is the graph of given vector function, okay? Now, let me try to figure out the direction of motion, okay? You can choose any t value, okay? So for my convenience, let me choose t is equal to 1, okay? You can use any t value, okay? Then we can find the position of object on the graph, okay? By plugging in 1 into r, which is 1 comma 1 square. That means when the parameter t is equal to 1, your particle on the graph must be 1 comma 1. I'm talking about this point. Okay? Then what about the velocity? Direction is concerned with velocity, right? So let me use different color, okay? Direction is concerned with r prime of 1, right? Wait a minute. So we didn't find r prime, okay? Here we go. What is r prime t? As I told you, just take the derivative component-wise, right? And your x component is t, then t prime is 1. And y component, t squared prime is 2t. This is your r prime, and this will give you the direction, okay? So let me plug in 1 in there. Then it is equal to 1 comma 2 times 1, which is 1 comma 2. What does that mean? At this point, the direction vector is 1 comma 2, which means 1 run and 2 rise. So it will be tangent line definitely. And this vector r prime 1, which is 1, 2. Okay? So what does that mean? It is tangent vector, and also like it is the velocity, or we can say it is like direction of motion. Okay? So your particle at this point, your particle want to go this way, but keep that in mind. Your particle must be on the graph. Okay? Which means it is tempting to use like moving this way, then your particle is moving up like this way. Okay? This is the direction of motion. Okay?